Howdy everyone, this is Boone, and today I'll be going through the most common type of tidal currents problem, which is a tidal current velocity problem. As you can see from this list of tidal current problems that I have made, the velocity problems, velocity and direction problems make up the majority of the list. That is why I will be going through problem 1207 today in this video. Problem 1207 says, what will be the velocity of the tidal current at New London Harbor entrance, Connecticut at 16:15 Eastern Standard Time Z+5 on 26 December 1983? A lot of information there, so let's try to unpack it up. First piece of relevant information that we find is that it was on the 26th. And let me pull up my view a little bit smaller. Both the information might work. 26 December 83, like the rest of these problems. Our location is New London Harbor entrance, and because we're going to be copying and pasting that, I will just be abbreviated to New London Harbor entrance ET. That's 16:15 Eastern Standard Time DD+5. Then I'm gonna write over here DD check. This will remind me to make sure the ZD of New London Harbor entrance lines up to ZD+5, or or if it doesn't, I need to make adjustments. But this is not a daylight savings problem. All right, from here, we're just gonna copy New London Harbor entrance like this and go to our reprints. That looks like this on the first page. F. New London Harbor entrance. Only 2 entries go up when we push Control Find. And since this is the back half of the book, as discussed in navigation of the reprints video that I made, we know that this is a tidal current problem. We scroll down a little bit more, and we're able to see New London Harbor entrance. This has a lot of information that we need to know. Now, since this is strictly a velocity problem and not a velocity and direction problem, there is some information on here that we want me to write down for this problem, but is a good idea to write down for future problems. So it's just good to have to write down every time. So our reference station. Scroll up a little bit, and we see it on the race. The big thing we care about right here is what page it's on. 34. A little bit more, and we can see that this information right here kind of looks similar to the tide of heights problem, but minimum before flood, flood, minimum before ebb. That lines up with this information right here, right here in order. Then speed ratios, this column. Then the maximum flood direction, this column right here, maximum ebb direction, right here, and maximum ebb direction is right over here. So all 3 of these pieces of information can be found here on this table 2, which on the PDF is located on 213. So minimum before ebb for New London Harbor entrance is -1H, 22 minutes. The flood is going to be -1H, 51 minutes. The minimum before ebb is going to be negative 2h, 12 minutes. The ebb is going to be negative 1h, 15 minutes. Now, the speed ratios are very important. And as we can see right here, for the lunar harbor engines, both of them are 0.1. So I'll write down 0.1, 0. Now our third piece of information we need is maximum flow direction. Maximum flow direction is this column and this column. It lines up with the order that has it on here. So this box right here for maximum flow direction will be 348, and maximum ebb will be 211. All right, now this is all of our substation input that we need to have to make this problem work. Now, just like the type heights problem, we're going to go to the reference station and put in the numbers that we need. Since this is on the race, you go to page 34. We're in the back half of the problem, and the book is not cut correctly. We'll have to do a little bit of searching. So you see I've just been going up a little bit using my mouse cursor, bring me to page 34 of tidal currents, page 164 of the P. You know this isn't a tide of heights section because it is past 138, which is our currents part of the book. Now what I'm going to do is turn off my live cam, and we're going to find it. This is the 26th of December, A3 race. We're going to scroll down. And we are now on page 169. 160. Let's highlight 26th of December so we don't have the other one. Alright, now that we have that, zoom in on those numbers. Now I'm going to do what I've done in previous videos. Bigger. This will work one more time. Alrighty. For our reference station, we are trying to solve for after 1615. We need to account for this time right here. As you can pretty much tell though, there's only between two times that this problem could realistically work, 1649 and 2016. So on this side, skip a line, I'll put 1649 and 2016 on a 3.6 ebb. Now, why did I skip a line, you might ask? In case this actually wasn't the way it worked out, then I would have to add more numbers here to find the difference between this max and that number. So it's always good to leave yourself a little bit of room. But let's add in or subtract ebbs and floods for the problem. Since this is only ebbs, we're not going to be using the floods at all. 16. And now we're going to subtract 2, 12, and 2016. We're going to subtract 1, 15. So 49 minus 12, 37. 16 2016 are 15 minutes. So 1, 20 minus 1 is 9. Make it 9. Now, the speed ratio, we use our velocity and multiply it by either ebb or flood. This is ebb and 0.1. 3.6 times 0.1 is 3.6 is 0.36. But since we are doing tide type problems, we need to round this number up to the nearest tenth, which would make this of 0.4 ebb. Now we have our reference station and our substation, New London Harbor entrance, accounted for. 0.4 ebb, and between these two times, 1615 does work. If I did mess up, I would have both of these make up for them. Now, we need to find the interval between slack and the desired time. That is not too bad because slack is this column. And our desired time is 1615. So it would be 1615 minus 1437, which we're going to hour 15, 60 minutes is 75, 75, 37, 38, 15 minus 14 is 01. The interval between slack and desired time is 01, 30 minutes. Interval between slack and maximum current. Well, this is our maximum, our slack. So we're going to subtract 1901 and 1437. Our way, 61. 61 minus 37 is going to be 24. And 18 minus 14 is 04. We get 04H 24 minutes. Maximum current, our maximum value between those two, whatever two numbers you're using. Our case would be 0.4 ebb. Now, just like tidal height problems, we also for tidal current. Looks like. Now there's two parts to this. Table A, which represents everything not found in Table B. Table B has the following locations: Cape Cod Canal, Hell's Gate, Chesapeake, Delaware Canal, and all other stations in which Table 2 are referenced to them. So, since New London Harbor entrance is not referenced to any of these, we're going to be using Table A. Table A, and look at what our given information is. The given information is that our interval between slack and desired time is 1 hour 38 minutes. Slack, desired time, so that would be 1 hour 40. And slack and maximum current is going to be 4 hours. 24 rounds down to 20, so right here. So, just like we did in the other table 3, we're going to go to 1 hour 40. This column, show you guys as best I can. Let's get worried. Cross all the way until we see that is exactly 0.6. Now that we have the fact that it's 0.6, we're going to put that right here, because that is a factor. Now, to find our velocity, all we have to do is one last step. Take our maximum current, 0.4, and we multiply it, 0.6. Multiply those together, you get 0.24. Since tidal current only uses, and tidal heights only uses a 10th decimal place, we're going to round down, 0.2. do not. Now, double check our answer. We're going to come back over to additional questions. 5 cam. See, have 0 point knots as the correct answer. This is the most common type of problem that you will see throughout all of the current tidal current. Once I get more information on what problems we'll be covering on the test, I will make more videos regarding those topics. Thanks for watching.